Hello all, welcome to my course on methods of adhesion measurement theory and practice. We are at lecture 51 today and we are discussing about the bending of thin plate and an adhesive which is sandwiched between a thin plate and a rigid substrate. So, today we will discuss about how to measure adhesion using an experiment which is based on the topic that I covered in the last lecture. So, this is called the lift-off experiment for measuring adhesion strength. So, in particular what we have here is this rigid plate and this elastic adhesive film. So, this is basically an adhesive film and we bring in contact a thin flexible cover plate. So, this is a flexible plate and we apply a load over here to, so we bring in contact this flexible plate. So, this flexible plate adheres to this adhesive and then we apply a load over here to drive this point of contact. So, in a sense we keep either we apply load or keep the spacer over here. So, keep this height, maintain this height. So, let us say this is delta and as a result of this balance forces, this contact line, okay, actually this line is basically a contact line. So, the film is actually like this, but contact line, okay, that kind of moves and then comes at a specific point. And we know this distance at which this contact point lies from this point of application of the load or this point of placing this spacer. So, say this distance is a over here. So, this is a over here, this is delta, that is known. The elastic modulus, Poisson ratio and all these things are known, and by balancing these forces one should be able to find out the adhesion energy, okay, or the strength of this interface, that is the idea. So, I will describe that in detail. So, that is about this lift-off experiment for measuring the adhesion strength, and this is there actually in my paper measuring the work of adhesion between soft confinement film flexible plate. You can have a look at it in this particular paper what I am going to talk about. So, let us say an infinitesimal small rectangle over here and this is the EXS, the strain we can obtain, the horizontal strain, and this is W is the vertical strain, and we are considering the plane strain approximation. So, remember this is the y direction. So, plane strain in the y axis, that is what we are defining. So, we know xx, zz, xz we can define. So, basically this is the picture over here and it so happens that this rigidity of the flexible D, okay, of this plate is such that the bending is indeed very small. So, if you want to obtain that what will be this bending angle, let us say this will be less than or about a degree, 1 or 2 degrees at the most. Okay. So, this plate thickness let us say about 150 to 200 micron. To give you some feel, this spacer delta height will also be about let us say 200 micron, something like this. So, indeed this bending is very small and this plate can be a microscope cover slip by the way, and this is the adhesive. So, these are some model adhesive that but we can use any adhesive which is in this analysis this is elastic. Okay. Adhesives are not in general elastic, can be viscoelastic, but in all our analysis we are keeping it simple and so we are considering it is elastic. So, this contact line is there established because of equilibrium of forces, that is what I have said. So, the stress equilibrium relation for an incompressible film in the plane strain approximation in terms of pressure field we have already defined it. So, it was, remember, it was mu into del square u by del x square plus del square u by del z square. Okay. This is equal to del p by del x. We had obtained that, and mu into del square w by del x square plus del square w by del z square. Okay. That is equal to, this is del p by del z. So, we had obtained this stress equilibrium relations, okay, for an incompressible film in plane strain approximation in terms of pressure field. Okay. We have obtained that. Please review this lecture 42 you will get all this. And the incompressible relation will be obtained as del u by del x plus del w by del z. So, this is equal to 0. This is this incompressibility relation. So, that also we obtain. So, our film is incompressible, that is all it means. If it is not incompressible, then also can be done, but for the time being let us consider it to be incompressible. So, we need to solve this equation, and we know that we want to see that which terms are more significant, because it is a partial differential equation, it is not easy to solve analytically. So, but we can do that, but making some suitable assumptions which are valid assumptions, let us say, and that we can obtain by doing what is known as the dimension analysis. So, we did all that in some previous lecture, I think lecture 42, 43 like that. So, dimension analysis we did. In dimension analysis we can find out that among these terms which are more significant and which can be neglected, like that. So, you will do all that, and if you remember, we had shown that by this dimension analysis that it is these the following terms which are of significance. So, del square u by del square is equal to del p by del x, and 0 is equal to del p by del z. So, for these two equations. So, after dimension analysis and then using this what is known as the lubrication approximation. Lubrication approximation means that it is the h is the characteristic length scale in the thickness direction, and L is the characteristic length scale in the lateral direction or x direction. So, this quantity much smaller than 1. So, this is this lubrication approximation. So, use that along with the dimension analysis, and we could obtain this simple equation. So, here it is simple because it becomes del b by del z is equal to 0 along the thickness of this film. So, what it means is that the pressure within this film is uniform as far as z axis is concerned, and of course, it is uniform on the y axis. So, only thing the p depends upon is along the x. So, here instead of del p by del x we can write also dp by dx, because pressure no longer depends upon z and y. So, that is what we had done it, and here also as far as this film is concerned, for this film we can write this equation. The boundary conditions can also be obtained. So, the boundary condition like that. So, the film remains strongly bonded to this particular substrate over here. So, yeah, let me write it here. So, the film remains strongly bonded over here. So, therefore, z is equal to 0, u is equal to 0, and w also equal to 0, and at z is equal to h. So, that means at this thickness. So, this is the film and this is the h. So, let me draw it little bit magnified way. So, this is this z is equal to 0 and z is equal to h is the film surface. So, there this at z is equal to h, continuity has to be maintained where the plate and the film is in contact. So, let us say this is at x is equal to 0, x is equal to 0. So, the film remains contact with the plate at x less than equal to 0. So, in this regime the deflection or the deformation of the film and the plate are same. So, what it means is that at z is equal to h, at z is equal to h and x less than equal to 0, the Vw is equal to zeta of the plate. So, at z is equal to h, W should be equal to zeta, because it is a flexible plate, it is not a rigid plate, it deforms. So, this zeta is a function of x here. So, W will be like this, and also the continuity of the normal stress will be there. So, therefore, it will be continuity will be normal stress. So, that will be equal to sigma zz will be equal to minus p plus 2 mu del W by del Z, like that. So, this is sigma zz. So, sigma zz, so this is P is the pressure in the film, and this is sigma zz, that is the normal stress. Now, this is at z is equal to h, and this should be equal to what? So, this should be equal to the bending force on this particular plate. So, that should be equal to, it should be equal to actually minus of, because it will be minus here. So, it will be minus of d into del 4 or d4, let us say d4 d4 by dx4 or like that. So, this is this quantity, this is the bending force on this particular plate. Remember that the plate is in contact with this thin elastic film. Okay. So, that this is plate is in contact with this thin elastic film. So, this is, let us say, x is equal to 0. So, in this region, okay, this plate is subjected to distributed load, okay, and here in this region, okay, this is the distributed load which is non-zero, distributed load, okay, and over here in this region there is no load, okay, there is zero load. However, here at the end, that means over here, okay, there is the spacer there. So, the spacer gives it a concentrated load, okay. So, it is like that. So, this particular problem, as far as this plate is concerned, so the plate is subjected to distributed load at x less than equal to 0, okay, and at from x is equal to 0 to a. So, this is x is equal to a, remember x is equal to a, let us say here it is a. So, at x is equal to a, the plate is subjected to this concentrated load. So, so we have actually, as far as this plate is concerned, we have actually two regimes. In one regime, this is subjected to distributed load, another regime it is subjected to concentrated load, and of course, the plate is bending in such a manner the continuity is being maintained at x is equal to 0. So, we will come to that. So, this is the way the situation is. So, I am trying to explain you the physical situation here, and the maths will follow. So, in this region, okay, in this region, let us say at any x, the stress, normal stress in the film and the bending force, that has to be equal. So, therefore, this particular equation that comes, and we will show that in a minute. So, sigma Zz equal to minus P plus 2 mu. So, P is the pressure in the film. Now, for the film outside, so the film and the plate at x 0 to x to a, as I said, this is equal to 0, and so sigma Zz is given as minus of 2 sigma minus of d into del 4 zeta by del x4, as I wrote over here, sigma z is equal to this quantity. Now, if we do the dimensional analysis, you will see that this quantity will fall out, because this is very small with respect to this pressure here, and so here therefore, we have this P is equal to, therefore, we will have from here the boundary condition as P is equal to, so P is the pressure in the film, hydrostatic pressure in the film, so that is equal to d into, okay, d4 zeta by dx4. That will be the equation that we have to see. So, P we have to obtain from this stress equilibrium relations within the film, that is what we are doing here. So, this I have already said that at z is equal to h, this W will be equal to zeta, and this is the stress balance, and there is another thing, that is U at z is equal to h is equal to 0, because this is the no slip boundary condition. So, no slip contact we are considering at z is equal to h. So, therefore, U is at z is equal to h is equal to 0. So, that is also there. So, now we can integrate these equations that we have derived, these equations. This equation we derived after simplification, we can integrate, and I will go to that directly. We have already done these things, I am skipping that. And so, integration of these equations, for example, this equation will yield U is equal to 1 by this will be 2 mu, 1 by 2 mu. So, it is 1 by mu, this del square, so del p by del x. So, it will be actually z square minus z h into dp by dx. So, here we just integrate it and use this boundary condition that at z is equal to h, u is equal to 0, and z is equal to 0, u is equal to 0. So, it will lead to this expression. So, u is equal to this, and we can obtain del w by del z equal to minus of del u by del x. From there, this is from the incompressibility relation. So, minus 1 by 2 mu z square minus z h, and this is d square p by dx square. So, therefore, w, no, it is w by del z actually, sorry about that, del z. So, w is equal to minus, this is 1 by 2 mu and this is z cube by 3 minus z square h by 2, and this is d square p by dx square plus some constant that will be there. So, at z is equal to 0, okay, w is equal to 0. So, therefore, c will be equal to 0, and at z is equal to h, w is equal to zeta. So, therefore, zeta is equal to here minus this is h cube by 3, it is h cube by 2. So, it is 2h cube by 6 minus h cube and minus plus. So, h cube by 12 mu, this is d square p by dx square. So, this will be the conditions, the equation. Now, this is the pressure over here. Now, this is the boundary condition at P, we have already obtained. So, that is P is equal to, remember that P is equal to, so this minus will go here because it is minus minus plus. So, P is equal to D, and this is d4 zeta by dx4. So, therefore, from here this is d square p by dx square. So, it is d square p by dx square. So, this is equal to d, and this is d6 zeta by dx6. So, therefore, this zeta, okay, will be equal to, so zeta will be equal to zeta. So, that will be equal to here d zeta h dh cube by 12 mu, dh cube by 12 mu, and this is d6 zeta by dx 6. It will be like that. And here, of course, I have here I have already written this, and a and b are equal to 0, that I have already obtained. It is z square minus hz. So, I have written z, that is fine, I have written it correctly, no issues. So, here this will be therefore z square by 2 mu, and put p is equal to d, this quantity. So, that is actually equal to d into d5 zeta by dx to the power 5 into z square minus zh, right. So, u will be given by like this. So, it is 1 by 2 mu here, and no, it is 1 by 2 mu here, and it is d here, and this is d4 zeta by dx4. So, it is, you have to derive it, del p by del x is there. So, therefore, it is like this. This is the expression for u, and expression for w will be equal to, I have already obtained it here, it will be equal to minus by minus of 1 by 2 mu, let us say minus, it is d by 2 mu, and it will be d6 zeta by dx 6, and here it will be z cube by 3 minus this is z square by h by 2, like that, and that is already there, it is here, and just substitute p is equal to d4 zeta by dx4. So, it is like this. So, here, so these are the expressions for u, w, and this is the expression for zeta. So, remember zeta is the deformation of the plate. So, this is from x less than 0, at x greater than 0 or 0 to x to a, for this portion, for this plane, for this plate, remember that is equal to 0 here. So, this is d and d4 zeta by dx4, this is equal to 0. So, we have actually two equations for zeta, as I said earlier, as I already said. So, there are two regimes of bending for this flexible cover plate. So, one is at x less than or equal to 0, where the load is distributed, and another is 0 to x to a, where the load is actually concentrated, because for this case the load is applied at x is equal to a. So, we have to apply now, we have to now solve these two equations. So, here. So, let us, so you have actually these two equations to solve, right, because here it is d into d4, so d is goes, so therefore, only I have written only this quantity. So, these two equations are to be solved, and see there are this is the 6th order equation, this is the 4th order equation. So, we need to require in a sense 6 plus 4 10 boundary conditions to solve for zeta over the whole range, okay, minus infinity to a. So, from x less than 0 we need 6 boundary conditions, and then the for x is equal to a total we need 10 boundary conditions, that is it. So, 3 boundary conditions can be obtained at x tending to minus infinity, where we can say that the deflection deformation that is zeta, okay, will be equal to 0, the slope of zeta will also be equal to 0, and it is not, actually I have changed the symbol, I should not have changed that, it should be zeta, actually I will maintain here zeta, x that is equal to 0, and the curvature there is also continuous. So, del cube by zeta by del x cube, that also equal to 0. So, I hope I am getting the right thing. Yeah, I mean like first order, second order, okay, that should be equal to 0. So, it is first derivative, second derivative, okay, all these terms be equal to 0. So, remember that, actually I should write it here. So, here like that. So, 3 boundary conditions we obtain at the plate, flexible plate, away from the contact line, okay. So, the deformation of the flexible plate must vanish far away from the contact line. So, basically this is the plate and this is the film. So, x tends to infinity, minus infinity is towards this, at this end, right. So, 3 boundary conditions. Now, at x is equal to 0, okay, what we can say is, let us say that it should be continuous, the plate should bend continuous. So, basically zeta will be equal to 0, so should be equal. So, it is x equal to 0 minus, let us say x is equal to 0 minus, this will be equal to zeta x is equal to 0 plus, then the slope should be continuous. So, del zeta or d zeta dx at x is equal to 0 minus should be equal to d zeta by dx, x is equal to 0 plus, and then the curvature. So, means the torque is also continuous. So, therefore, d square zeta by dx square at x is equal to 0 minus should be equal to d square zeta by dx square at x is equal to 0 plus, and then the shear force that is applied on the plate, that is also continuous, and I have not gone through that, but we can say the shear force is the cubic derivative. So, it is d cube z by zeta by dx cube at x is equal to 0 minus should be equal to d cube zeta by dx cube at x is equal to 0 plus. So, at x is equal to 0 at this point, okay, all these boundary conditions should hold. So, 3 conditions here, there are 4 conditions. So, 7 conditions done. Now, at this end, at x is equal to a, okay, x is equal to, there are 2 boundary conditions because it is freely supported there. So, I have already said about that. At x is equal to a, this zeta curvature is 0. So, d square zeta by dx square equal to 0, and also either zeta is given. So, this is at x is equal to a. So, let us say that zeta at x is equal to a. So, that is equal to that spacer height that is given. So, the spacer height is delta, that is given. So, that is delta is given, let us say, or let us say the force is given. So, if the force is given, then we have to use this boundary condition minus f and d cube and zeta dx cube at x is equal to a, and this is sorry about that, minus d here, this is minus d here, and this is equal to f. So, like that. So, we have either this condition or we have this condition. So, we have already talked about that. So, this will be equal to this will be there. So, there are 2 boundary conditions we obtain. So, 3 here, 4 here and 2 here. So, we have 9 boundary conditions, and the 10th boundary condition comes that since that it is getting separated at this particular point. So, therefore, the pressure has to be maximum at this point. So, del p by del x equal to 0, del p by del x will be equal to 0. So, that will be the fourth one and the 10th one. So, the ninth boundary condition I have already said here. So, this is 3 plus 4 7 plus 2 here 9, and then the this boundary condition is over here. So, this gives d into this is d4 zeta by dx4, but it is derivative. So, it is d4 d5 zeta by dx5 equal to 0. So, this is the this will be the boundary condition here. So, like that. So, this is the 10 boundary condition. So, we need these 10 boundary conditions that we have here, and therefore, we can solve this equation, this 2 equations that we have in terms of zeta, and we can obtain this solution. So, remember that this is a 6th order equation at x less than 0. So, there are actually 6 terms will be there, 6 integration constants. So, after using all those integration constants, okay, we will be left with this 1, 2 and 3 terms over here. So, there is an exponential quantity over here, and there are sine functions and cos functions over here. And at 0 to x to a, this zeta of x is given by this. So, now what this solution means is that at x less than 0, at x is less than 0. So, that means this is the plate. So, it remains in contact with this particular film, let us say, with this film. So, what it means is that at x less than 0, the deformation of this particular plate is sinusoidal, but with exponentially decreasing amplitude. So, this solution is not straight but it is sinusoidal actually. Okay? We will describe that what exactly it will look like, and with a exponentially decreasing amplitude, because remember x is negative over here. So, as x increases, negative x increases, this term becomes smaller. So, the amplitude decreases. So, the deflection here in this region, this is actually sinusoidal, okay, with sine function and cos functions there, but with exponentially decreasing amplitude, that is all it means. And over here from 0 to x to a, okay, this is this polynomial equation, cubic equation, that is all it is. Now, here if you see this particular term k, so let me describe here. K has an inverse length scale, and k will be given as k inverse is a, so k is a inverse length scale. So, k inverse has got a characteristic length scale. So, k inverse is given as dh cube by 12 mu whole to the power 1 upon 6. So, let us check it. So, d has unit of Newton meter and h is a unit of meter cube, and this is Newton per meter square. So, you see this is 3 into plus 1 4 to 6, so 1 by 6. So, this has a length scale of meter, dimension of length, k inverse. So, k inverse is a characteristic length, okay, and this f inverse, there is expression for f inverse also. I have not written it here, but f inverse also has an expression, and that also is a characteristic length scale which is given over here. So, f dash, okay, defines the response of this plate. What is k inverse? I will describe it in a minute. So, f dash represents that given one delta, what is the kind of response that is there in the plate. So, that is all it is. And what is k inverse? That can also be obtained. So, here I will obtain directly. So, here if you plot this zeta by f dash, so this is this expression, this curve. So, this is decreases, then it increases once again, decrease. So, you see this is varying oscillatory, okay. So, this is an oscillation with sine and cosine function as I said, and then the amplitude decreases. So, that is all it shows. So, initially it is a tensile region, and then there is compression, and then tensile again, like that. So, that also shows up in the stress, normal stress calculation, okay, that you can do by obtaining minus d del 4 zeta by del x 4, we can obtain that, and we get this expression that also captures that effect. So, here this oscillation has got a characteristic wavelength, okay. This wavelength is defined by this particular length scale k inverse. So, this wavelength lambda comes out to be close to about 5.6 into K inverse. That is all it means, and that is irrespective of any plate, irrespective of any other factors. So, how much load is applied and all that. This is this K inverse, that is given as I wrote here, d h cube by 12 mu whole to the power 1 upon 6, right, that is fixed for this particular film and this particular cover plate. So, it depends upon the modulus of the shear modulus of the film and thickness of the film, right, and d depends upon the flexural rigidity of this cover plate. So, it is a function of both material and the geometric properties, and yeah, this is the way it is given us, and this determines what will be the wavelength of this oscillation. Now, we can also obtain the sigma zz by this quantity as I said, and this is given by this function, this equation, that is also oscillation. So, it is tensile here, it is maximum tensile at x is equal to 0, and then it goes on becoming compression, then tensile and compression again on like that. So, this is the way the solution comes, and now these solutions can now be used for obtaining the expression for the work of adhesion, and I will take it up in the next lecture. Thank you.